So I've had some questions from students asking about, they weren't sure what equation to use and when to use that equation. So to start, I always suggest, to look at what, are you asked, and what are you given, and what are you looking for? And then also the other thing that is important to remember or to know is what a lot of these symbols stand for. And so, c is the speed of light. Hopefully we all know that. We've also got wavelength. We've also got our frequency. And what are some other ones that we can look at? Frequency, right? We've got Q is our heat, W is our work, N is our quantum level. Those are going to be the main ones. Oh, H, Planck's constant, right? So it helps to have an idea of what some of these stand for. And remember, I will give you Planck's constant, I will give you Rydberg's constant, and I will give you the speed of light. So you don't have to worry about remembering those, just what they stand for. So here's where I would kind of look at things, right? If we're given a frequency or we're given a wavelength and, asked to find frequency, we're clearly going to be using C equals wavelength times frequency. Or if we're given a frequency and asked to find energy, we're clearly going to be using energy equals Planck's constant times frequency. And similarly, as I said, these two equations go together an awful lot. If you're given frequency and asked to find wavelength, if you're given energy and asked to find wavelength, sure, you're going to have to use this equation first with Planck's constant to find your frequency. Once you know frequency, you can plug it in over here to find your wavelength. So these two equations are very important, and it's going to be important to remember. Anytime you see wavelength or frequency, you're probably going to be using these two equations. Our next equation down is kinetic energy equals 1/2 mass times velocity. Sure, we covered this briefly in the chapter, but we didn't do any calculations with it. There really wasn't any homework to do with it, so I would take that as your hint of how likely you are to use the calculation for kinetic energy. Total energy, however, we spent a lot of time in the change of energy as a result of heat and work being done. So if you're given a question where the reaction lost X amount of heat or the reaction did X amount of work energy, then this equation should pop in your head. I'm given a unit, I'm given values for heat, I'm given values for work, so I must be looking at our change in energy. And then to look at two other equations real quick that we can cancel out, right? We did nothing, we talked about it, but we didn't do much with pressure volume calculations. So, again, I said I provide you all the equations that are provided for that chapter. So I'm going to provide you these equations. Are you likely to use them? Probably not. Next, however, is a important calculation. So Q equals our specific heat times our mass times our delta T. So are you given a mass? Are you given a energy with respect to joules? Or are you given a change in temperature? If you're given three, of these variables, there's a pretty good chance you're going to use Q equals C times M times delta T. And then the version of this, if you're given moles, right? Q equals molar heat capacity times N, where N is our number of moles, times your same delta T. As for our delta H of formation, right? You're going to be given a table of delta H's of formation for a reaction, and basically said you need to put those together with respect to the delta H's of our products and the delta H's of our reactants, and then take into account the molar amount of each of those. So you're going to multiply X number of moles of product times its delta H, and then do the summation of that, add all of those delta H's together minus the summation of how many moles of each reactant do I have times the delta H of that reactant. So again, you're going to be looking for a table of delta H values, and you're going to be asked to calculate the delta H for the reaction. Let's see, 3 more equations we had to look at. So this is the de Broglie wavelength. This is the equation we use to calculate the wavelength of a baseball, for example, moving 60 miles an hour, that example we did in class, where, again, you'd be given mass, or might be looking for the wavelength given mass and frequency, and then h is Planck's constant. But again, with these other 2 calculations where frequency shows up, there's no mass variable. So if mass does show up, there's a pretty good chance you're going to have to use the de Broglie equation for wavelength. And then the last place that energy shows up is, these 2 equations are related, is either we're finding the energy of our quantum level. So in this case, with a quantum level, right, they're going to tell us, an electron at quantum level 3, what is the energy of that level? So we just need to know that n equals our quantum level. So 1 over 3 squared times Planck's constant times the speed of light times Rydberg constant is the energy at that level. If, however, we're doing a transition between levels, they would say an electron at n equals 6 goes to an electron, or goes to a quantum level of n equals 4. What's the change in energy? So all we need is to remember this equation, and that, right, n is our quantum levels, n initial is where we started. So if we started at energy level 6, we'd do 1 over 6 squared, and final would be where we finished. And if we finished at quantum level 4, it would be 1 over 4 squared. So if you're given energy, or if you're asked to find energy in given quantum levels, right, this is the only equation, these 2 equations are the only 2 that work with respect to a quantum level of energy. So I hope that helps kind of clear up some of the questions people had about what formula to use and when.